Imagine you have two identical clocks. Same manufacturer, same mechanism, same perfect calibration. You place one on the floor and the other on a high shelf. You wait, and when you compare them, they disagree. Not because one is broken, not because of a manufacturing defect. Both clocks are telling the truth. Both are measuring time correctly. But gravity itself has changed what correctly means for each of them. The clock on the floor, closer to Earth's mass, has genuinely experienced less time than the clock on the shelf. This is not a thought experiment. This has been measured with atomic clocks precise enough to detect the difference across a height of just 1 foot. Time itself runs at different rates depending on where you are in a gravitational field. And tonight, we're going to understand exactly why. If you find these kinds of deep explorations fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it means a lot to me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let's start with something you have probably never questioned. Time. You experience it constantly. Every second that passes, you feel it. Every minute that slips by, you are aware of it. Time is the background rhythm of everything you do. It is there when you wake up. It is there when you fall asleep. It never stops. It never hesitates. And here is the thing that seems most obvious about it. Time passes at the same rate for everyone. If you and a friend are sitting in the same room, time is moving at the same speed for both of you. If your friend flies across the country and comes back, you both experience the same amount of time while apart. A minute for you was a minute for them. A second for you was a second for them. That seems so obvious it barely feels worth saying. Time is time. It does not play favorites. It does not speed up for one person and slow down for another. It is the most reliable, the most consistent, the most universal thing in existence. Or at least, that is what every human being who ever lived assumed for thousands of years. And they were wrong. Not slightly wrong, not wrong in some trivial, technical way that only matters inside a physics laboratory. Wrong in a deep, fundamental sense that affects everything about how the universe actually works. Time does not pass at the same rate everywhere. Two clocks sitting at different heights in a gravitational field will tick at genuinely different rates. The clock that is lower, closer to the source of gravity, will accumulate less time than the clock that is higher up. And the key word here is genuinely. This is not a problem with the clocks. It is not a glitch. It is not some subtle mechanical error caused by pressure or temperature or vibration. Both clocks are working perfectly. Both are measuring time exactly as they should. The disagreement between them is real because time itself is passing at different rates at their two locations. Gravity does not just pull on things, it changes the rate at which time flows. And that is one of the most unsettling discoveries in the history of science. For most of human history, nobody had any reason to doubt that time was universal. The idea that time might behave differently depending on where you are would have sounded like nonsense. Isaac Newton, whose laws of motion and gravity dominated physics for over 2 centuries, treated time as absolute. In Newton's universe, there was a single cosmic clock ticking away in the background, marking the same seconds for every object and every observer in the universe. A second on the surface of Earth was the same as a second on the surface of Jupiter, which was the same as a second in empty space 1 billion miles from anything. Time was a stage on which events played out, but the stage itself never changed. Newton wrote about this explicitly. He called it absolute, true, and mathematical time, flowing equally without relation to anything external. Time was the one thing you could count on to be the same everywhere and always. And for everyday life, Newton was right enough. The differences in how time passes at different locations in a gravitational field are so incredibly small under normal conditions that no human being could ever notice them without extraordinarily precise instruments. You will never feel time passing differently when you walk upstairs versus downstairs. Your wristwatch will not show a noticeable difference whether you wear it on the ground floor or on the roof. The effect exists, but it is tiny, absurdly tiny. Under the conditions of everyday life on Earth, the difference in the rate of time between your feet and your head is so small that you would need to wait longer than the current age of the universe for it to add up to even 1 full second. So Newton was not foolish for assuming time was absolute. He was working with the best information available and the best instruments available, and at the scales he could measure, time appeared perfectly uniform. The problem only becomes visible when you have instruments precise enough to detect the incredibly subtle differences, or when you are dealing with gravitational fields far stronger than anything on Earth's surface. The first person to realize that time might not be universal was Albert Einstein. In 1915, Einstein published his general theory of relativity, a radical reimagining of gravity that replaced Newton's invisible force with something far stranger. We will get into the details of what Einstein actually proposed shortly, but the relevant prediction for right now is this. Einstein's equations showed that time passes more slowly in stronger gravitational fields. A clock sitting on the surface of Earth, deep in Earth's gravitational well, should tick slightly slower than a clock floating in space, far from any massive object. A clock on the ground floor should tick slightly slower than a clock on the top floor of a tall building. The deeper you are in a gravitational field, the slower time passes for you compared to someone higher up. When Einstein first proposed this, it was purely theoretical. Nobody had instruments precise enough to test it. Clocks in 1915 were accurate to maybe a few seconds per day. The differences Einstein was predicting were billionths of a second over hours or days. There was simply no way to measure such tiny effects with the technology of the early 20th century. The best clocks available were mechanical, relying on pendulums or springs or carefully machined gears. These instruments were extraordinary feats of engineering, but they drifted. Temperature changes expanded or contracted the metal components. Humidity affected the lubricants. Vibration disturbed the mechanisms. Even the finest mechanical clocks in the world varied by seconds per day, sometimes more. And Einstein was predicting effects measured in billionths of a second. It was as if someone had predicted that a specific grain of sand on a beach weighed slightly more than the grain next to it, and the only scale available could not detect anything smaller than a boulder. So for decades, gravitational time dilation remained a prediction, a mathematically elegant, deeply strange prediction that most physicists believed was probably correct, but that nobody could confirm directly. The breakthrough that eventually made testing possible was not a new theory. It was a new kind of clock, the atomic clock. The idea behind an atomic clock is fundamentally different from every timekeeping device that came before it. A pendulum clock counts swings. A quartz watch counts vibrations of a crystal. Both depend on physical objects whose properties can change. A pendulum's length changes with temperature. A quartz crystal ages and drifts over time. But atoms do not change. A cesium atom today is identical to a cesium atom a billion years ago. It has the same mass, the same structure, the same energy levels. And when a cesium atom transitions between two specific energy states, it emits or absorbs radiation at an extraordinarily precise and unchanging frequency. This frequency, this rate of oscillation, is a property of the atom itself, determined by the fundamental constants of the universe. It does not drift. It does not age. It does not depend on temperature, or pressure, or humidity. A cesium atom oscillates at exactly 9,192,631,770 times per second. This number is so precise and so stable that in 1967, the international scientific community redefined the second itself based on it. 1 second is no longer defined by the rotation of Earth or the swing of a pendulum. 1 second is exactly that many oscillations of a cesium atom. The atom became the clock. And that clock was stable enough to detect what Einstein had predicted half a century earlier. Two physicists named Joseph Huffeler and Richard Keating decided to test Einstein's prediction in the most direct way possible. In 1971, they took 4 cesium beam atomic clocks, placed them on commercial airline flights, and flew them around the world. That was the experiment. Fly clocks on airplanes and see if they agree with identical clocks that stayed on the ground. The clocks they used were accurate to about 1 second in hundreds of thousands of years, far more precise than any timekeeping device Newton could have imagined. Huffeler and Keating flew their 4 atomic clocks eastward around the world on commercial flights, then flew them westward around the world on separate flights. The whole thing cost about $8,000 in 1971 money, which included buying the clocks their own airplane seats because the clocks were too large and delicate to go in the cargo hold. When the flying clocks returned and were compared to the reference clocks that had stayed at the United States Naval Observatory in Washington, the results were exactly what Einstein had predicted decades earlier. The clocks disagreed. On the eastward trip, the flying clocks had lost about 59 nanoseconds compared to the ground clocks. On the westward trip, the flying clocks had gained about 273 nanoseconds. A nanosecond is 1 billionth of a second. These are unimaginably small amounts of time. You could not perceive a nanosecond if your life depended on it. A nanosecond is to 1 second what 1 second is to roughly 31 years. But the differences were there, clearly measured, clearly real, and they matched Einstein's predictions. Now, there is an important subtlety here that we will explore in more detail later. The time differences in the Huffeler-Keating experiment were caused by 2 separate effects. One was gravitational time dilation. The airplanes were flying at high altitude, roughly 10 kilometers above the ground. At that height, the clocks were farther from Earth's center of mass, higher up in Earth's gravitational field, and therefore ticking slightly faster than the clocks on the ground. The other effect was velocity-based time dilation from special relativity. The airplanes were moving, and moving clocks tick slightly slower than stationary ones. These 2 effects combined in different ways for the eastward and westward flights, which is why the numbers were different. But both effects were present, both were measurable, and both confirmed Einstein's predictions. The universe does not treat time as absolute. Gravity and motion both change how time passes, and this experiment proved it. But the Huffeler-Keating experiment, as groundbreaking as it was, measured tiny differences under relatively mild conditions. The gravitational field at airplane cruising altitude is only very slightly weaker than at the surface. The difference in clock rates is absurdly small. You might be tempted to dismiss this as a curiosity, an interesting fact with no practical consequences, something that only matters to physicists running exotic experiments. But you would be wrong. Because gravitational time dilation affects a technology you almost certainly use every single day. GPS, the Global Positioning System. GPS works by using a constellation of satellites orbiting Earth. As of 2026, there are about 31 operational GPS satellites, each orbiting at an altitude of roughly 20,200 kilometers above the surface. Each satellite carries multiple atomic clocks on board. When your phone calculates your position, it receives signals from at least 4 of these satellites simultaneously. Each signal contains the exact time it was sent, according to the satellite's onboard clock and the satellite's precise position in orbit. Your phone compares the arrival times of these signals and uses the tiny differences to triangulate your position on the surface. The entire system depends on extremely precise timing. Light travels about 30 centimeters in 1 nanosecond. That means a timing error of just 1 nanosecond translates to a position error of about 30 centimeters. A timing error of 1 microsecond, which is 1/1,000,000th of a second, would mean a position error of about 300 meters. And a timing error that accumulated over the course of a full day without correction would make the entire system useless. Here is where gravitational time dilation becomes a practical engineering problem. The GPS satellites orbit at about 20,200 kilometers altitude. At that height, they are significantly farther from Earth's center of mass than clocks on the surface. They are higher in the gravitational field, and because of gravitational time dilation, the atomic clocks on those satellites tick faster than identical clocks on the ground. Not by a lot. The difference is about 45 microseconds per day. The satellite clocks gain roughly 45 millionths of a second every day compared to ground clocks, purely because of their position in the gravitational field. At the same time, the satellites are moving at about 3,900 meters per second in their orbits. This orbital velocity causes a velocity-based time dilation effect that makes the satellite clocks tick slightly slower, by about 7 microseconds per day. So you have two competing effects. Gravity makes the satellite clocks run faster by about 45 microseconds per day. Velocity makes them run slower by about 7 microseconds per day. The gravitational effect wins. The net result is that GPS satellite clocks gain approximately 38 microseconds per day compared to clocks on the surface of Earth. 38 microseconds per day might not sound like much, but remember, light travels about 30 centimeters per nanosecond. 38 microseconds is 38,000 nanoseconds. If GPS did not account for relativistic time dilation, the position errors would accumulate at a rate of roughly 10 kilometers per day. Within a single day, your GPS would be off by 10 kilometers. Within a week, it would be off by 70 kilometers. The system would be completely, utterly useless. Every GPS satellite has its clock rate adjusted before launch to compensate for both gravitational and velocity time dilation. The clocks are deliberately set to tick at a slightly wrong rate on the ground, so that when they reach orbit, where gravity and velocity alter the flow of time, they tick at the correct rate relative to ground-based clocks. This correction is not optional. It is not a minor adjustment. Without it, GPS simply does not work. Every time you use your phone to navigate to a restaurant, every time a plane lands using GPS guidance, every time an emergency service locates a caller, the system is silently correcting for the fact that time passes at a different rate in orbit than it does on the surface of Earth. You are relying on Einstein's general relativity every single day, whether you know it or not. But physicists were not satisfied with measuring gravitational time dilation at the scale of airplane altitudes or satellite orbits. They wanted to know how precise the effect really is. They wanted to push the limits of measurement, to see whether Einstein's predictions held up at smaller and smaller scales under less and less extreme conditions. And in the past 2 decades, atomic clocks have become so astonishingly precise that they have confirmed gravitational time dilation at scales that would have seemed impossible just a generation ago. The key was a new generation of clocks that went far beyond cesium: optical clocks. Instead of counting microwave oscillations from cesium atoms, optical clocks count oscillations of light emitted by atoms like aluminum, strontium, or ytterbium. Light oscillates far faster than microwaves, hundreds of trillions of times per second, compared to roughly 9 billion for cesium. This is like replacing a ruler marked in inches with one marked in thousandths of an inch. More ticks per second means finer resolution, more precision, more ability to detect vanishingly small differences. In 2010, physicists at the National Institute of Standards and Technology used this new generation of clocks to demonstrate something remarkable. They measured gravitational time dilation across a height difference of just 33 centimeters, about 1 foot. They used aluminum ion clocks, trapping individual aluminum ions in electromagnetic fields and counting the oscillations of light they emitted. These clocks were so stable that they would need to run for over 1 billion years before drifting by a single second. The experiment required extraordinary care. Every source of error had to be identified and eliminated. Temperature fluctuations in the laboratory could cause the metal components of the apparatus to expand or contract by fractions of a nanometer, which would shift the frequencies. Vibrations from traffic outside the building, from air conditioning systems, from footsteps in the hallway, all of these had to be isolated and suppressed. Electric and magnetic fields from nearby equipment had to be shielded. The physicists were not just building a clock, they were building the most controlled environment in human history, a place where every possible disturbance was reduced to the point where the only remaining effect was the one they wanted to measure. The quiet whisper of gravity itself, changing the rate of time across a single foot of height. And they succeeded. They showed that a clock raised by roughly 1 foot above another clock ticked at a measurably different rate. The difference was incredibly small. We are talking about a change in clock rate of about 4 parts in 10 to the 17th power. That is a 4 preceded by 16 zeros after the decimal point. But it was there, measured, confirmed, repeatable. Then in 2022, a team at GLAR, a research institute at the University of Colorado, pushed even further. Using an optical lattice clock based on strontium atoms, they measured gravitational time dilation across a height difference of roughly 1 millimeter. 1 millimeter, the width of a pencil tip. This experiment was different from the aluminum ion approach. Instead of trapping a single ion, the strontium lattice clock trapped tens of thousands of strontium atoms in a grid made of intersecting laser beams. The atoms sat in this lattice like eggs in a carton, each one held in place by light. By comparing atoms at slightly different heights within the same lattice, the team could detect time dilation across an almost negligible distance. The clocks they used were so precise that they would not gain or lose a single second in roughly 15 billion years, which is longer than the current age of the universe. At that level of precision, the subtle warping of time by Earth's gravity becomes visible even across the tiniest height differences. When the results were published, they confirmed that even across 1 millimeter, time passes at a measurably different rate. The universe does not stop curving spacetime just because the distance is small. Gravity warps time everywhere, at every scale, down to the smallest separations we can measure. Think about what this means. Right now, as you sit or stand wherever you are, time is passing at a slightly different rate at the level of your head compared to the level of your feet. Your head is farther from Earth's center of mass than your feet. The gravitational field is very slightly weaker at your head, and because of that, time is moving very slightly faster for your head than for your feet. Not by an amount you could ever perceive, not by an amount that matters for your daily life in any practical sense, but the effect is real. It has been measured. It is not theoretical. It is not a mathematical abstraction. It is a feature of the universe you live in. And this is the crucial point that needs to be completely clear before we go any further. When we say gravity changes the rate of time, we do not mean that gravity mechanically interferes with clocks. We do not mean that the gears run slower, or the pendulum swings slower, or the cesium atoms vibrate differently because gravity is tugging on them. If that were the case, you could build a clock that was immune to gravity. You could design a mechanism that compensated for the gravitational pull and kept perfect time regardless of where you placed it. But you cannot. Because gravity is not interfering with the clock's mechanism. Gravity is changing time itself. Everything runs slower, deeper in a gravitational field. Atomic vibrations, chemical reactions, biological processes. the speed at which electrical signals travel along your neurons. Every physical process that takes time, which is every physical process, period, runs at a different rate depending on where it is in a gravitational field. If you lived your entire life at sea level and your identical twin lived their entire life on top of a tall mountain, and then you compared your biological ages after decades, the twin on the mountain would be very, very slightly older. Not because mountain air is different, not because of diet or exercise or stress, but because time itself passed at a slightly faster rate at the top of the mountain than at sea level. The difference would be far too small to detect biologically, probably amounting to a fraction of a microsecond over an entire lifetime. But it would be there. It is real. It is not a metaphor. It is not a way of speaking. It is a literal physical fact about the universe. This is what we mean when we say time stops matching itself near gravity. We do not mean time turns off. We do not mean time freezes. We do not mean that anyone standing in a gravitational field perceives time as being weird or distorted. Locally, everything feels perfectly normal. If you are the clock on the ground floor, you do not feel time passing slowly. Your seconds feel like seconds. Your heart beats at its normal rate. Nothing seems strange. And the clock upstairs also feels perfectly normal to itself. Its seconds feel like seconds too. The strangeness only appears when you compare. When the two clocks are brought together and their readings are checked against each other, they disagree. They have measured different amounts of elapsed time, and both of them are right. There is no error. There is no malfunctioning clock. Time genuinely passed at different rates at their two locations. The disagreement is the reality. This raises a question that should be nagging at you by now. Why? Why on earth would gravity change the rate at which time passes? Gravity is supposed to be a force that pulls things toward massive objects. It makes apples fall from trees. It keeps planets in orbit. It holds you to the ground. What does any of that have to do with time? How can a force that acts on matter also act on time itself? And that question is exactly the right one to ask, because the answer to that question is going to require us to completely rethink what gravity actually is. The picture of gravity you carry in your head, the picture most people carry, is almost certainly wrong. Not wrong in the details, but wrong in the most fundamental way possible. Gravity is not what Newton said it was. It is not a force that reaches across space and pulls objects together. It is something far stranger, far more elegant, and far more deeply connected to the nature of time than you ever imagined. And understanding that connection is the only way to understand why two perfect clocks can disagree, why time stops matching itself near gravity, and why this is not a flaw in the universe, but a feature built into the very structure of reality. You have lived your entire life with a mental picture of gravity. That picture probably looks something like this. There is a force that reaches out from massive objects and pulls other objects toward them. Earth pulls you downward. The sun pulls the planets inward. The moon pulls on the oceans and creates tides. Gravity is a force of attraction that acts across space, an invisible rope connecting every object with mass to every other object with mass. This picture comes from Isaac Newton. In 1687, Newton published his law of universal gravitation, which stated that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Double the distance and the force drops to 1/4. Triple the distance and it drops to 1/9. This law was extraordinary. It unified the motion of falling apples and orbiting planets into a single mathematical framework. For the first time in history, the same equation that described a rock falling to the ground also described the moon orbiting Earth and Earth orbiting the sun. Gravity was universal. It acted the same way everywhere. And Newton's equation let you calculate its effects with stunning precision. Newton's gravity works beautifully. It predicted the orbits of planets. It explained the tides. It allowed engineers to calculate trajectories for cannonballs and later for rockets. When NASA sent astronauts to the moon, the trajectory calculations were done using Newtonian gravity. For nearly every practical purpose you will ever encounter, Newton's description of gravity is more than good enough. But Newton himself knew something was wrong with his own theory. He could describe what gravity does with perfect mathematical precision, but he could not explain how it works. How does Earth know the Sun is there? How does the gravitational force travel across 93 million miles of empty space? What carries it? What mediates it? Newton had no answer. He famously wrote that the idea of gravity acting at a distance through empty space without any medium to carry it was, in his words, so great an absurdity that he believed no one who had a competent ability for thinking could ever accept it. He described the math. He admitted he could not explain the mechanism. And for over 200 years, nobody else could either. Enter Albert Einstein. In 1907, 2 years after publishing his special theory of relativity, Einstein had what he later described as the happiest thought of his life. He was sitting in a chair at the patent office in Bern, Switzerland, and he imagined a person falling from the roof of a building. This sounds morbid, but the physics is extraordinary. Einstein realized that a person in free fall would not feel their own weight. If you are falling freely, everything around you is falling at the same rate. You, your clothes, the air around you, any objects you are holding, all of it accelerates downward together. There is no relative motion between you and your surroundings. You feel weightless. This is exactly the same experience astronauts have on the International Space Station. They are not outside the reach of gravity. The station orbits at about 400 kilometers altitude, where Earth's gravitational pull is only about 11% weaker than at the surface. The astronauts float not because gravity is absent, but because they are in free fall. The station and everything inside it are falling toward Earth together. They just happen to be moving sideways fast enough that they keep missing. Their path curves around Earth in an orbit. But locally, inside the station, the experience is identical to having no gravity at all. You float. Objects float. Water forms spheres in mid-air. There is no experiment you can perform inside a sealed falling box that will tell you whether you are in free fall near a massive object or floating in deep space far from any source of gravity. The physics inside the box is the same in both cases. This is called the equivalence principle, and it does not just work in one direction. Einstein realized it cuts both ways. If free fall is indistinguishable from the absence of gravity, then standing on solid ground must be indistinguishable from being accelerated. Think about this carefully. Right now, you are probably sitting or standing on the surface of Earth. You feel your weight pressing you into your chair or pressing your feet against the floor. You feel gravity pulling you down. But Einstein said something radical. He said that what you are actually feeling is not a force pulling you down. What you are feeling is the ground pushing you up. The surface of Earth is accelerating you upward, not through space in the usual sense, but through space-time. You are being prevented from following your natural path, which would be free fall. If the floor disappeared, you would fall. You would be weightless. You would follow the path that gravity dictates, a path of free fall, and you would feel nothing. No force, no weight, no acceleration. The fact that you feel weight right now means something is interfering with your natural motion. The ground is pushing you away from the path you would naturally follow. This flips everything upside down. In Newton's picture, standing on the ground is the default state. You are at rest. Gravity is pulling you down, and the ground is holding you up. The force of gravity is the active agent. The ground is just a passive support. But in Einstein's picture, free fall is the default state. Falling is the natural motion. It is what objects do when nothing interferes. Standing on the ground is the unnatural state. You are being accelerated away from your natural trajectory by the electromagnetic forces in the ground, pushing against the electromagnetic forces in your feet. Gravity is not pulling you down. The floor is pushing you up. And this distinction, which sounds like philosophical hair-splitting, turns out to be the key to understanding everything about gravitational time dilation. Because if free fall is the natural state of motion, if objects in free fall are not being acted upon by any force, then what is gravity? If it is not a force, what is it? Einstein's answer, which he worked out over the next 8 years and published in 1915 as the general theory of relativity, is that gravity is geometry. Gravity is the shape of space-time itself. To understand this, we need to talk about space-time. You already know what space is. It is the three-dimensional arena in which things exist. Objects have positions in space. They can be above, below, to the left, to the right, in front, or behind. 3 dimensions. You also know what time is, or at least you think you do. It is the dimension in which events happen. Things occur before, after, or at the same moment as other things. 1 dimension. In 1908, the mathematician Hermann Minkowski, who had actually been one of Einstein's teachers, showed that space and time are not separate things. They are woven together into a single 4-dimensional fabric called spacetime. An event is not just a location in space, it is a location in spacetime. It has 3 spatial coordinates and 1 time coordinate. Where something happens and when something happens are aspects of the same underlying structure. This was not just a mathematical convenience, it reflected something deep about reality. Space and time are connected. What one observer measures as a distance in space, another observer moving at a different velocity might measure partly as distance in space and partly as an interval in time. Space and time mix together depending on your motion. They are not independent. They are components of a single 4-dimensional continuum. Now here is the core of general relativity. Mass and energy cause space-time to curve. Not just space, space-time. The entire 4-dimensional fabric warps and bends in the presence of mass. Earth does not reach out and pull you toward it with an invisible force. Earth warps the space-time around it, and you move through that warped space-time. What you perceive as gravity is your response to the curved geometry of the space-time you are traveling through. You have probably heard the rubber sheet analogy. Imagine stretching a rubber sheet flat and placing a heavy ball on it. The ball creates a dip, a depression in the sheet. If you roll a marble across the sheet, the marble curves toward the heavy ball, not because the ball is pulling on it with a force, but because the surface it is rolling on is curved. The marble is just following the shape of the surface. This analogy is useful, but also misleading in important ways. For one thing, the rubber sheet is a 2-dimensional surface sitting in 3-dimensional space. Real space-time is 4-dimensional and is not sitting inside anything. There is no higher dimensional space that space-time curves into. Space-time is all there is, and it curves within itself. More importantly, the rubber sheet analogy only shows the curvature of space. But gravity curves time as well, and it is specifically the curvature of the time dimension that is responsible for most of what we experience as gravity in everyday life. This is so important that I want you to really sit with it. When you stand on the surface of Earth and feel your own weight, the dominant effect is not the curvature of space. The curvature of space near Earth's surface is extremely subtle. If you measured the geometry of space around Earth very carefully, you would find that it deviates from flat geometry by an incredibly small amount. Parallel lines that should never meet according to flat geometry would eventually converge, but only after travelling enormous distances. The spatial curvature near Earth is almost negligible. What is not negligible is the curvature of time. Near a massive object, time itself is warped, and this warping of time is what causes objects to fall. It is what creates the sensation of weight. It is what makes you feel like something is pulling you toward the ground. Here is how to think about this. Everything moves through space-time. Even when you are standing perfectly still in space, not moving an inch, you are still moving through time. You are aging. Seconds are passing. You are traveling through the time dimension at a rate of 1 second per second. That is your motion through space-time when you are stationary in space. All of your motion is directed along the time axis. Now, near a massive object like Earth, the time dimension is curved. It is not straight and uniform. It is warped by the presence of mass. The curvature of time near Earth means that the direction of forward in time is not the same everywhere. It is slightly tilted, and that tilt points toward the center of Earth. When you are in freefall, you are following the straightest possible path through this curved space-time. You are doing the four-dimensional equivalent of walking in a straight line. But because time itself is curved and tilted toward the mass, the straightest path through space-time happens to be a path that curves toward Earth in space. You are not being pulled by a force. You are following the straightest available path through curved geometry, and that path leads toward the ground. Let me make this more concrete with a specific example. Imagine you are holding a ball at shoulder height and you let go. In Newton's picture, the explanation is simple. Gravity exerts a force on the ball, pulling it downward. The ball accelerates toward the ground at about 9.8 meters per second. Force causes acceleration. That is Newton's second law. Clear and intuitive. Now here is Einstein's explanation of the exact same event. Before you let go, the ball is stationary in space. But it is not stationary in space-time. It is moving through time. Every object, whether it is moving through space or not, is always moving through space-time because time never stops. The ball, sitting still in your hand, is traveling forward through the time dimension. Now you release it. No force acts on the ball anymore. Your hand was pushing it upward, holding it off its natural path, and now that push is gone. The ball is free. It follows its geodesic, the straightest possible path through the curved space-time around Earth. And here is what is crucial. Because the time dimension near Earth's surface is curved, tilted toward the center of Earth, the straightest path through space-time for that ball is not a path that stays at the same height. It is a path that moves toward the ground. The ball does not fall because something pulls it. The ball falls because falling is the straightest line through the curved time around Earth. From the ball's perspective, it is not accelerating. It is in free fall. It feels no force. If the ball had a tiny accelerometer inside it, that accelerometer would read 0 during the fall. The ball is doing nothing. It is simply existing in curved space-time, following the geometry, going straight. It is the ground that is doing something. The ground is accelerating upward through space-time, and eventually the ground and the ball meet. We call that meeting an impact. But in Einstein's picture, it is the ground that rushed up to meet the ball, not the ball that was pulled down to the ground. This is not a different way of describing the same physics. It is a genuinely different physical picture with different measurable predictions. Newton's picture and Einstein's picture agree for almost every everyday situation, which is why Newton's gravity worked so well for centuries. But they disagree in extreme situations and in their predictions about time. Newton's gravity has no reason to predict that time should flow differently at different heights. There is nothing in his equations that connects the force of gravity to the rate of time. But in Einstein's picture, the connection is automatic. If the time dimension is curved, if the direction of forward in time is tilted differently at different heights, then the amount of time that elapses along paths at different heights must be different. Gravitational time dilation is not an extra prediction tacked onto general relativity. It is the most basic consequence of what gravity is in this framework. Gravity curves time. Curved time means different amounts of time at different locations. That is why clocks disagree. This is what physicists call a geodesic. A geodesic is the straightest possible path through a curved space. On a flat surface, a geodesic is a straight line. On the curved surface of Earth, a geodesic is a great circle, the kind of path an airplane follows on a long flight. The airplane is not curving left or right, it is following the straightest path available on a curved surface. In spacetime, a geodesic is the path an object follows when no force acts on it. When you are in freefall, you are on a geodesic. You are following the natural geometry of spacetime. You feel no force because no force is acting on you. You are just following the shape of reality. When you stand on the ground pushes you off your geodesic. It forces you away from the straightest path through spacetime. That is why you feel weight. You feel weight not because gravity is pulling you, but because the ground is pushing you away from the path spacetime wants you to follow. Now we can finally understand why gravity changes the rate of time. And this is the crucial mechanism that everything in this story depends on. Near a massive object, spacetime is curved. The time dimension is warped, and the specific way it is warped means that the passage of time is different at different locations. A clock deeper in the gravitational field, closer to the mass, is sitting in a region of spacetime where the geometry is more warped. The curvature is stronger. And in that more strongly curved region, less time elapses along any given path compared to the same path in a less curved region farther from the mass. This is not because gravity is doing something to the clock. It is because the clock is embedded in spacetime, and the spacetime it is embedded in has a different shape at different locations. The clock on the ground floor and the clock on the top floor are both moving through spacetime. Both are following paths through the time dimension, but the spacetime they are moving through has a different geometry at their two locations. The geometry near the ground is more curved, more warped by Earth's mass, and in that more warped geometry, less time elapses. The clock is not running slow. Time is shorter there. It is a geometric fact about the region of spacetime the clock occupies. Think of it this way. Imagine two people walking side by side across a flat field. They walk at exactly the same pace and cover exactly the same distance. Now imagine the field is not flat. Imagine one person walks along a straight path while the other walks along a path that curves and winds. Even if both people walk at the same pace, the person on the curved path covers a different amount of ground. Their path is a different shape. In spacetime, something similar happens. Two clocks at different heights in a gravitational field are both moving forward through time, but the spacetime they are moving through has different geometry at their two locations. The clock deeper in the field is moving through more curved spacetime, and in that curved geometry, the path through time is shorter. Less time elapses. Not because the clock is broken, and not because something is slowing it down, because the geometry of spacetime at that location is such that less time exists along that path. This is what Einstein's field equations describe. They are equations that relate the distribution of mass and energy to the curvature of spacetime. You tell the equations where the mass is, and the equations tell you what shape spacetime has in that region. And from that shape, you can calculate everything. How objects move, how light bends, and how much time elapses at every point. The field equations do not describe a force, they describe geometry. Gravity is not a force in general relativity. It is the curvature of space-time, and all its effects, including the warping of time, follow from that geometry. This is why you cannot build a clock that is immune to gravitational time dilation. Every clock, no matter how it works, whether it uses atoms, light, pendulums, springs, or any other mechanism, must operate within space-time. And if the space-time it occupies is curved, then the time available for it to tick is different from the time available for a clock in a less curved region. You cannot shield a clock from this effect because you would have to shield it from space-time itself. And space-time is not something outside the clock. It is the framework within which the clock exists. The clock does not sit in space-time the way a boat sits in water. The clock is part of space-time. Its atoms are embedded in space-time. Its electrons move through space-time. Its vibrations oscillate through space-time. Changing the geometry of space-time changes everything about the clock, because everything about the clock depends on the space-time it is made of. This also explains why everyone experiences their own local time as perfectly normal. If you are the clock on the ground floor, all your physical processes are running in the same curved space-time. Your atoms, your neurons, your thoughts, your heartbeat, everything is embedded in the same geometry. Everything is consistently affected. From your perspective, nothing is unusual. 1 second feels like 1 second. Your watch ticks normally. Your coffee cools at the expected rate. Your conversations happen at normal speed. There is nothing inside your experience that tells you time is passing differently for you than for someone upstairs. The only way to discover the difference is to compare, to bring the two clocks together, or to send signals between them and see that they have accumulated different amounts of time. The mismatch is not something either clock can detect on its own. It only appears in the relationship between clocks at different locations. This is what makes gravitational time dilation so subtle and so profound at the same time. It is invisible from the inside and undeniable from the outside. Let me address something that might be bothering you. If gravity is not a force, if it is just the geometry of space-time, then why does it feel like a force? Why does it feel like something is pulling you down? The answer is that what you feel is not gravity. What you feel is the ground pushing you. When you stand on a floor, the atoms in the floor exert electromagnetic forces on the atoms in your feet. Those forces push you upward, away from the geodesic path you would naturally follow through curved space-time. You feel this push as weight. It is identical in every way to the sensation you would feel if you were standing in a rocket accelerating upward in empty space, far from any massive object. In the rocket, there is genuinely a force pushing you. The floor of the rocket is accelerating upward and pushing you along with it. You feel weight. You feel pressed into the floor. And no experiment you can perform inside the rocket will tell you whether you are in a rocket accelerating in empty space or standing on the surface of a planet. The physics is identical. This is the equivalence principle again. What you feel as gravity is actually the sensation of being accelerated away from freefall. Real gravity, the curvature of space-time, is something you cannot feel at all. The only way to be in pure gravity, free from all other forces, is to be in free fall. And in free fall, you feel nothing. You float. You are weightless. You are following the geometry of space-time without interference, and that feels like no force at all. This is a completely different way of understanding reality. In Newton's universe, space and time are a fixed, flat, unchanging stage. Objects move on that stage and forces act between them. Gravity is one of those forces, reaching across space to pull objects together. In Einstein's universe, there is no fixed stage. The stage itself is dynamic. It curves, it warps. It responds to the presence of mass and energy. Objects do not get pulled by forces. They follow the natural paths through a curved stage. And because the stage includes time as well as space, the curvature affects not just where things go, but when things happen. Time is part of the geometry, and where the geometry is more curved, time is different. Not broken, not slowed by some external influence, just different. Geometrically, structurally, fundamentally different. This is why time stops matching itself near gravity. Not because gravity reaches out and tampers with clocks. Not because there is some mysterious force acting on the mechanism of timekeeping, but because gravity is the curvature of space-time. And curved space-time has different amounts of time at different locations. A clock deeper in the field is in a region where space-time geometry dictates that less time passes. A clock higher up is in a region where space-time geometry dictates that more time passes. Both clocks are faithfully measuring the time that exists at their locations, and those amounts are different. The disagreement between them is not an error. It is a direct measurement of the curvature of space-time between them. Every time two clocks at different heights disagree, they are telling you something about the shape of the universe. They are measuring geometry. The geometry of space-time itself. And this is just the beginning. Because so far, we have only been talking about the gentle, subtle curvature caused by Earth. The differences are real, but tiny. Nanoseconds over hours, microseconds over days. You need atomic clocks, accurate to fractions of a billionth of a second, to detect them. But the mechanism that causes these tiny differences is the same mechanism that operates everywhere in the universe, at every scale, in every gravitational field. And when you move from the mild gravity of Earth to the extreme gravity near the densest objects in the universe, this same effect grows from a subtle measurement curiosity into something dramatic, something that warps time so powerfully that it reshapes our understanding of what is possible in this universe. But before we go there is another piece of this puzzle we need to examine. Because gravitational time dilation is not the only way time can stop matching itself. There is another kind of time mismatch, one that comes not from gravity, but from motion. And understanding how these two effects relate to each other is essential to seeing the full picture of why time behaves the way it does. So far, we have been talking about one way time can stop matching itself: gravitational time dilation. Clocks at different heights in a gravitational field tick at different rates because the geometry of space-time is curved by mass. The deeper you are in the gravitational field, the more curved the space-time, and the less time elapses along your path. This is a consequence of general relativity, Einstein's theory of gravity, published in 1915. But there is another way time can stop matching itself, and Einstein discovered this one first. 10 years before general relativity, in 1905, Einstein published his special theory of relativity. And special relativity revealed something just as shocking. Two clocks moving at different velocities will also disagree about how much time has passed. Not because of gravity, not because of the curvature of space-time, but because of motion itself. If you take two identical clocks, leave one sitting on a table, and send the other one racing across the room and back at high speed, the moving clock will have measured less elapsed time than the stationary one when they are reunited. The faster the clock moved, the greater the disagreement. This is velocity-based time dilation. And just like gravitational time dilation, it is not a problem with the clock. It is not caused by vibration or acceleration or mechanical stress. Time itself passes at a different rate for the moving clock. Every physical process on board, atomic vibrations, chemical reactions, biological aging. Everything runs slower from the perspective of the stationary observer. This might sound like we are just describing the same effect twice. Gravity slows time. Motion slows time. Are they the same thing with different names? They are not. They arise from different aspects of spacetime, and understanding how they differ is essential to understanding why time behaves the way it does. Let me walk you through velocity-based time dilation first, and then we will see how the two effects relate. The key insight of special relativity is something we touched on briefly. The speed of light is the same for every observer, regardless of how they are moving. This is not intuitive. In everyday life, speeds add up. If you are on a train moving at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour relative to the train, someone standing on the platform sees the ball moving at 120 kilometers per hour. Speeds combine. That is how Newtonian physics works, and it matches our everyday experience perfectly. But light does not obey this rule. If you are on a spaceship moving at half the speed of light, and you turn on a flashlight, the light does not travel at 1.5 times the speed of light from the perspective of someone watching you. It still travels at exactly the speed of light, 300,000 kilometers per second. The same speed it always travels. Both you on the ship and the person watching you from outside measure the exact same speed for that beam of light. This seems impossible. If you are already moving at half the speed of light, how can the light you emit still be moving at the full speed of light relative to both you and a stationary observer? How can both measurements be correct? The answer is that space and time adjust themselves to keep the speed of light constant, and the way they adjust is through time dilation and length contraction. Here is what happens. When you move through space, you are diverting some of your motion through spacetime away from the time dimension and into the space dimensions. Everything moves through spacetime at the same total rate. This is a difficult concept, so let me try to make it concrete. When you are standing still, not moving through space at all of your motion through spacetime is directed along the time axis. You are moving through time at the maximum possible rate, 1 second per second. Time flows at its full speed for you. Now, suppose you start moving through space. You get in a car. You start walking. You board a rocket. Some of your motion through spacetime is now directed through space instead of through time. And because your total rate of motion through spacetime is fixed, the amount directed through time must decrease. You move through time more slowly. Your clocks tick slower. Your atoms vibrate slower. Everything about you runs a tiny bit slower compared to someone who is stationary. The faster you move through space, the more of your space-time motion is directed through space, and the less is directed through time. At everyday speeds, the effect is so small it is completely undetectable. Even the fastest human-made objects move at a tiny fraction of the speed of light, and the time dilation at those speeds is negligible. A car moving at 100 kilometers per hour experiences time dilation so small that you would need to drive for billions of years before your clock disagreed with a stationary clock by even 1 second. But as you approach the speed of light, the effect becomes dramatic. At 90% of the speed of light, time passes at about 44% of the rate it passes for a stationary observer. At 99% of the speed of light, time passes at about 14% of the normal rate. At 99.99% of the speed of light, time passes at less than 1.5% of the normal rate. You could travel for what feels like a few months, while decades pass for everyone you left behind. This has been measured directly. It is not speculation. Particle accelerators routinely observe time dilation. Muons are subatomic particles created when cosmic rays hit the upper atmosphere. Muons are unstable. They decay with a half-life of about 2.2 microseconds. At that rate, even travelling at nearly the speed of light, muons created in the upper atmosphere should decay long before reaching the ground. The distance is too great, and their lifetime is too short. And yet, muon detectors on the surface of Earth detect muons constantly. How? Because the muons are moving at roughly 99.9% of the speed of light, and at that speed, time dilation extends their effective lifetime enormously from the perspective of observers on the ground. What is 2.2 microseconds from the muon's own perspective becomes many times longer from our perspective, long enough for the muons to survive the journey to the ground. This is not a subtle effect. It is not ambiguous. Without time dilation, we would detect almost no muons at sea level. With time dilation, we detect exactly the number predicted by special relativity. The experiment matches the theory precisely. The early experimental evidence for velocity-based time dilation came even before muon measurements. In 1887, Albert Michelson and Edward Morley performed an experiment trying to detect the motion of Earth through a hypothetical medium called the luminiferous ether, which was thought to carry light waves. Their experiment failed to detect any motion through the ether. This null result was deeply puzzling and became one of the key experimental facts that special relativity explained. The Dutch physicist Hendrik Lorentz had already developed mathematical equations describing how time and space must transform between observers moving at different velocities in a way that keeps the speed of light constant. These equations, now called the Lorentz transformations, contain time dilation as a built-in feature. Einstein's genius was to realize that these transformations were not just mathematical tricks. They described the actual physical behavior of space and time. The speed of light really is constant for all observers, and space and time really do adjust to make this possible. So now we have two distinct effects that both cause time to stop matching itself. Gravitational time dilation, where clocks at different heights in a gravitational field tick at different rates because of the curvature of spacetime. And velocity-based time dilation, where clocks moving at different speeds tick at different rates because motion through space reduces motion through time. They have different causes. One comes from where you are in a gravitational field. The other comes from how fast you are moving. But they are not unrelated. They are both consequences of the same underlying reality, the structure of spacetime. General relativity contains special relativity as a special case. When spacetime is flat, when there is no gravity, general relativity reduces to special relativity. Velocity-based time dilation is what happens in flat spacetime when objects move relative to each other. Gravitational time dilation is what happens in curved spacetime even when objects are not moving relative to each other. Both effects emerge from the same mathematical framework. Both are features of spacetime geometry. They are two faces of the same coin. And there is a beautiful, real-world system that demonstrates both effects working simultaneously, competing against each other in a way that you can calculate and verify. That system is GPS, which we discussed earlier. But now we can understand the full picture. A GPS satellite orbits Earth at an altitude of roughly 20,200 kilometers. At that height, it is farther from Earth's center of mass than a clock on the surface. The space-time up there is less curved. Gravitational time dilation makes the satellite clock tick faster than a ground clock by about 45 microseconds per day. That is the gravitational effect. The clock is higher in the gravitational field, in less curved spacetime, so more time elapses for it. But the satellite is also moving. It orbits Earth at about 3,900 meters per second. That is fast by everyday standards, though still a tiny fraction of the speed of light. This orbital velocity causes velocity-based time dilation, which makes the satellite clock tick slower by about 7 microseconds per day. That is the velocity effect. The clock is moving through space, so less of its motion through spacetime is directed through time. The two effects push in opposite directions. Gravity makes the satellite clock run fast. Velocity makes it run slow, and they do not cancel out. The gravitational effect is larger. The net result is that the satellite clock gains about 38 microseconds per day, compared to a clock on the ground. GPS engineers account for both effects, adjusting the satellite clock frequencies before launch so that the gravitational speed-up and the velocity slowdown are both compensated. The fact that GPS works, that it gives you accurate positions, that it guides aircraft and ships and emergency vehicles, is direct physical proof that both kinds of time dilation are real and that we understand them quantitatively. Every time your phone tells you where you are, it is confirming Einstein. There is another experiment that confirmed gravitational time dilation directly and beautifully, and it deserves attention because of how elegant it is. In 1959 and 1960, Robert Pound and Glenn Rebka performed an experiment at Harvard University that measured gravitational time dilation over a height of just 22.6 meters, the height of a single building, the Jefferson Tower at Harvard. Here is what they did. They used gamma rays emitted by radioactive iron-57. When an atom of iron-57 decays, it emits a gamma ray photon with a very specific, very precise frequency. This frequency is determined by the energy difference between two quantum states of the nucleus. It is extraordinarily well defined. They placed a gamma ray source at the bottom of the tower and a gamma ray detector at the top, 22.6 meters higher. Then they measured whether the frequency of the gamma rays changed as they climbed through the gravitational field. General relativity predicts that a photon climbing out of a gravitational field will lose energy. Not because something is pulling it back, but because of the difference in space-time geometry between the bottom and the top. A photon emitted in a region where time runs slower arrives in a region where time runs faster. The photon's frequency, which is the number of wave crests passing a point per second, was set by the conditions at the bottom. But at the top, where clocks tick faster and more seconds elapse for the same stretch of spacetime, the photon's frequency appears lower. Fewer crests per second from the top clock's perspective. This is called gravitational redshift. The photon has not slowed down. It still travels at the speed of light, but its frequency is lower when observed from a higher point in the gravitational field. And frequency is directly related to energy. Lower frequency means lower energy. The photon arrives at the top with slightly less energy than it had at the bottom. The connection to space-time geometry is direct and precise. The photon is a messenger, carrying information about the rate of time where it was born. It was emitted by an atom vibrating at a frequency set by the space-time geometry at the bottom of the tower. When it arrives at the top, the detector sits in space-time with a different geometry, a geometry where time passes slightly faster. The detector's own atoms vibrate at a slightly higher frequency than the source's atoms do, because the detector exists in a region with more available time per second. The arriving photon's frequency is now slightly too low to match the detector's atoms. It is redshifted. Not because anything happened to the photon during its climb, but because the space-time it left and the space-time it arrived in are genuinely different, with different amounts of time flowing at each location. The Pound-Rebka experiment does not merely demonstrate a quirk of clocks. It demonstrates that the fabric of space-time has a measurably different structure at the top of a building than at the bottom. The Pound-Rebka experiment measured this frequency shift. The predicted shift was tiny, about 2 parts in 10 to the 15th power, 2 quadrillionths. But by using a technique called the Mossbauer effect, which allows extremely precise measurements of gamma-ray frequencies, Pound and Rebka were able to detect it. Their result matched Einstein's prediction to within 10% on the first attempt. Later refinements of the experiment brought the agreement to within 1%. This was a direct measurement of gravitational time dilation over a height of less than 23 meters. It confirmed that time runs at a different rate at the top of a building than at the bottom. Not by much, but measurably, undeniably. The universe really does work this way. The Pound-Rebka experiment is especially important because it isolates gravitational time dilation from velocity effects. The source and the detector were both stationary relative to each other. Neither was moving. There was no velocity-based time dilation to worry about. The only variable was height in the gravitational field. And the only explanation for the measured frequency shift was the difference in the rate of time at the two heights. It was a clean, direct test of general relativity's prediction about gravity and time, and it passed beautifully. Now, I want to be very clear about something. When we talk about gravitational time dilation and velocity-based time dilation as two different effects, we are not saying they are caused by two different mechanisms operating on some shared underlying absolute time. There is no absolute time. That is the whole point. There is only spacetime, and the amount of time that elapses along a particular path through spacetime depends on the geometry of that path. Gravitational time dilation and velocity-based time dilation are both descriptions of how different paths through spacetime accumulate different amounts of time. In gravitational time dilation, two clocks at different heights are following different paths through curved spacetime, and the curvature means their paths accumulate different amounts of time. In velocity-based time dilation, two clocks moving at different speeds are following different paths through spacetime, even if it is flat, and the angles of their paths through the time and space dimensions mean different amounts of time elapse along each path. Think about it this way. Imagine two people starting at the same point on a map and walking to the same destination, but taking different routes. One takes a straight road, the other takes a winding, scenic route. They both end up at the same place, but the person on the scenic route has traveled a greater distance. Nobody says the scenic route stretched space, or that some mysterious force made the road longer. The routes were simply different shapes, and different shapes have different lengths. Spacetime works the same way, but with a twist that takes some getting used to. In spacetime, the equivalent of distance is proper time, the time measured by a clock travelling along a particular path. But here is the counterintuitive part. In ordinary space, a straight line is the shortest distance between 2 points. In spacetime, the relationship is reversed. A straight path, meaning a path where no forces act and the object moves only through time without acceleration or spatial detours, accumulates the most proper time. Any deviation from that straight path, whether caused by motion through space or by the curvature of gravity, results in less proper time. This is the opposite of what your spatial intuition expects. On a road map, detours make your trip longer. In spacetime, detours make your elapsed time shorter. Here is why this matters. When you are sitting still, not moving through space at all, you are on the straightest possible path through flat spacetime. All of your motion is directed through time. You accumulate proper time at the maximum rate. Now suppose you start moving through space. Your path through spacetime tilts. Some of your motion is now directed through space instead of through time. Your path is no longer the straightest one. It has a spatial component, a deviation. And because of the way spacetime geometry works, that tilted path accumulates less proper time than the straight one. The faster you move, the more tilted your path, and the less time you accumulate. That is velocity-based time dilation. Now consider gravity. You are sitting near a massive object. Even though you are not moving through space, the space-time around you is curved. Your path through time is no longer passing through flat geometry. It is passing through warped geometry. And warped geometry, like a tilted path, results in less accumulated proper time compared to a path through flatter spacetime farther from the mass. The deeper you are in the gravitational field, the more curved the spacetime, and the less time your path accumulates. That is gravitational time dilation. Both effects reduce your proper time compared to the maximum. Both are deviations from the ideal straight path through flat spacetime. One deviation comes from moving through space. The other comes from being in curved spacetime. But the underlying principle is identical. The amount of time your clock measures depends on the shape of your path through spacetime, and any path that is not the straightest possible path through flat spacetime will accumulate less time. Both effects are geometric. Both are about the shape of paths through spacetime. Neither involves a force acting on a clock. Neither involves some external agent tampering with the mechanism of timekeeping. They are features of the landscape of spacetime itself, as natural and as inevitable as the fact that a winding road is longer than a straight one. The distinction between the two effects is useful for practical calculations. When engineers design GPS, they calculate the gravitational correction and the velocity correction separately and add them together. That works because both effects are small under those conditions, and adding them gives the right answer to very high precision. But at a deeper level, they are not truly separate. They are both manifestations of the same underlying principle. The amount of time that passes for any clock depends on the path that clock follows through spacetime, and that path is shaped by both the curvature of spacetime and the clock's motion through it. There is one more thing I want to address here, because it is a source of enormous confusion. People sometimes hear about time dilation and think it is a kind of illusion, an appearance, a trick of measurement, something that looks like time is passing differently, but really is not. This is completely wrong. Time dilation is not an illusion. It is not an artifact of measurement. It is a physical reality with measurable physical consequences. The clocks that disagree have genuinely experienced different amounts of time. The muons that survive to reach the ground have genuinely lived longer from our frame of reference. The atoms on the GPS satellite have genuinely vibrated a different number of times than identical atoms on the ground. These are objective physical facts that all observers agree on. Here is a thought experiment that makes this vivid. Imagine you have a twin. You stay on Earth. Your twin boards a spacecraft that accelerates to 99% of the speed of light, travels to a star 10 light-years away, turns around, and comes back. From your perspective on Earth, the round trip takes a little over 20 years. But because of velocity-based time dilation, your twin's clocks, including their biological clock, have been running much slower. When they return, they have aged only about 2.8 years. You are now over 20 years older than when they left. Your twin is less than 3 years older. You are both standing in the same room, and you have aged differently. This is not an illusion. Your twin really is younger than you now. Their cells have divided fewer times. Their hair has grown less. Their heart has beaten fewer times. Time genuinely passed at a different rate for them. You can look at each other and see the difference. You can count the wrinkles, measure the telomere lengths, check any biological marker you want. The difference is real, physical, and permanent. And notice how this connects to the geometric picture. Your twin who travelled took a path through space-time that included a large spatial detour, out to a distant star and back. Their path was not straight. It curved through space and time in a way that accumulated less proper time than your path, which stayed mostly in one place, moving almost entirely through the time dimension. Both of you moved through space-time. Both of you accumulated proper time along your paths, but the shapes of your paths were different, and different shapes mean different amounts of elapsed time. Your twin's path with its enormous spatial component, accumulated less time. Your path, sitting on Earth, staying nearly straight through the time dimension, accumulated more. When you compare at the end, the difference is written in your bodies. This is not philosophy. This is geometry. The same is true for gravitational time dilation. Consider the atomic clocks on GPS satellites we discussed earlier. Those clocks are not moving through different space-time because of a force acting on them. They are simply sitting in a region where space-time has a different shape. The geometry up there is flatter, less warped by Earth's mass, and paths through that flatter geometry accumulate more proper time. That is why those clocks tick faster. Not because something is boosting them, but because the space-time they occupy has more available time per second built into its structure. Every extra microsecond those satellite clocks gain is proper time that genuinely elapsed along their path through less curved space-time. Proper time that simply does not exist along the more curved path of a clock on the ground. This should strike you as extraordinary. We are not talking about clocks being tricked or measurements being distorted. We are talking about the actual amount of time that exists along a path through space-time, depending on where that path goes and how it moves. The universe does not have a single universal clock ticking away in the background. There is no cosmic metronome keeping time for everyone. Every location, every path through space-time has its own amount of elapsed time, determined by the local geometry. And when those paths diverge and reconverge, when two clocks separate and come back together, the difference in their readings is a real, physical, permanent record of the different amounts of time that existed along their respective journeys. This is why understanding both kinds of time dilation matters. If you only knew about velocity-based time dilation, you might think time dilation was purely about motion, something that happens when things move fast. Interesting, but perhaps not deeply connected to the nature of space and time. But when you add gravitational time dilation, when you see that time also runs at different rates, at different heights, even when nothing is moving, the picture becomes much richer and much stranger. You realize that time dilation is not about motion in isolation, and it is not about gravity in isolation. It is about the structure of space-time itself. It is about the geometry of the universe. Every path through space-time has its own proper time, and that proper time depends on everything about the path. Its velocity, its position in a gravitational field, the curvature of space-time along its route, the angle of its trajectory through the 4 dimensions. And with that understanding firmly in place, we are ready to explore what happens when this effect is not subtle at all. When it is not a matter of nanoseconds or microseconds, when the curvature of space-time becomes so extreme, the gravitational field so intense, that time dilation grows from a tiny correction factor into a dramatic, universe-reshaping force. Because the same mechanism that makes your atomic clock on the ground floor tick a tiny fraction slower than the one on the shelf produces staggering effects near the densest objects in the cosmos. Objects where gravity curves space-time so severely that time itself slows to a crawl from the perspective of a distant observer. And understanding those extreme environments will show us just how far this principle can go and what it reveals about the deepest nature of reality. Everything we have discussed so far has involved gravity that is, by cosmic standards, gentle. Earth's gravity is real. It curves space-time. It makes clocks at different heights disagree. But the curvature Earth produces is extraordinarily subtle. The difference in the rate of time between your feet and your head is so small it takes the most precise instruments ever built to detect it. Even the difference between the surface of Earth and the orbit of a GPS satellite, a height gap of 20,000 kilometers, amounts to only about 45 microseconds per day. These are real effects with real consequences, but they are tiny. They are whispers of a mechanism that, under the right conditions, can roar. The universe contains objects so dense, so gravitationally extreme, that the same mechanism producing nanosecond differences on Earth produces time dilation so dramatic it defies everyday imagination. To see this mechanism at full power, we need to leave Earth behind and visit the densest objects in the cosmos. And as we do, the same principle will apply at every step. Time stops matching itself near gravity because space-time geometry is curved by mass, and the more mass is concentrated, the more severe the curvature, and the more dramatically time at different locations diverges. Let us start with white dwarfs. When a star like our Sun exhausts its nuclear fuel, it sheds its outer layers and leaves behind a dense core called a white dwarf. A typical white dwarf has roughly the mass of the Sun compressed into a sphere about the size of Earth. That is an extraordinary amount of compression. The Sun is about 109 times wider than Earth. Squeezing that much mass into an Earth-sized volume produces a density about 1,000,000 times greater than ordinary matter. A teaspoon of white dwarf material would weigh roughly 5 tons on Earth's surface. The gravitational field at the surface of a white dwarf is far stronger than anything on Earth. Surface gravity on a white dwarf is roughly 350,000 times the surface gravity of Earth. And because the gravitational field is much stronger, space-time is more severely curved near the surface. Time dilation at the surface of a typical white dwarf is measurably greater than on Earth. A clock on the surface of a white dwarf would tick about 0.03% slower than a clock far away in flat space-time. That might not sound like much, but compare it to Earth, where the effect is roughly 1 part in a billion. The white dwarf effect is millions of times stronger. Over the course of a single year, a clock on a white dwarf's surface would fall behind a distant clock by roughly 2.5 hours. This is no longer a matter of nanoseconds, this is hours per year. Measurable not with atomic clocks, but with an ordinary wristwatch if you could somehow survive on the surface, which you could not because the gravity would crush you instantly. We have actually measured gravitational time dilation from white dwarfs. Sirius B, the white dwarf companion to Sirius A, the brightest star in our night sky, has been studied extensively since its discovery. Light emitted from the surface of Sirius B is gravitationally redshifted. The photons climbing out of that intense gravitational field lose energy, their frequencies shifting toward the red end of the spectrum, exactly as general relativity predicts. The amount of redshift tells us how much spacetime is curved at the surface. It matches the predictions precisely. This is the same Pound-Rebka effect we discussed earlier, the same gravitational redshift measured across the height of a building at Harvard, but now observed across light years of space from the surface of a dead star. The same physics, the same mechanism, operating at a vastly greater intensity. But white dwarfs are just the beginning of extreme gravity. When stars significantly more massive than the Sun die, they can leave behind something far denser, a neutron star. When a massive star exhausts its fuel, it collapses catastrophically. The core implodes. Protons and electrons are crushed together so violently that they merge into neutrons. The entire core, containing more mass than our Sun, collapses into a sphere roughly 20 kilometers across. 20 kilometers. That is about the width of a city. A neutron star packs more than the mass of the Sun into a ball you could drive across in about 10 minutes. The density is staggering. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. The surface gravity of a neutron star is roughly 200 billion times the surface gravity of Earth. At this gravitational intensity, space-time curvature becomes severe. A clock on the surface of a neutron star would tick about 20 to 30% slower than than a clock far away in flat space-time, depending on the neutron star's exact mass and radius. This is no longer a subtle correction. This is not nanoseconds or hours. If you spent 1 year on the surface of a neutron star, a distant observer would measure that roughly 1.2 to 1.4 years had passed for them during your single year. Months of difference accumulating every year. Time is measurably, dramatically, unmistakably flowing at a different rate. And this has been observed. Neutron stars are real objects. We have detected thousands of them. Many are pulsars, rapidly rotating neutron stars that emit beams of radiation like cosmic lighthouses. As the neutron star spins, its beam sweeps across the sky. If Earth happens to be in the path of the beam, we detect a pulse of radiation each time the beam sweeps past. The pulses arrive with extraordinary regularity. Some pulsars are so stable that they rival atomic clocks in their precision, ticking away with a consistency that allows astronomers to detect variations of a few billionths of a second over years of observation. By studying those pulses, astronomers can measure the properties of the neutron star with remarkable accuracy. The timing of pulsar signals is affected by the gravitational time dilation at the neutron star's surface. When a pulsar is in a binary system orbiting another star, the signals it emits are affected by both its own gravitational field and by the gravitational field of its companion as it moves through different regions of curved spacetime during its orbit. When the pulsar swings close to its companion, deeper into the companion's gravitational well, its pulses arrive slightly delayed. When it swings farther away, they arrive slightly earlier. The pattern of these timing variations precisely matches the predictions of general relativity. By carefully analyzing them, astronomers have confirmed that Einstein's equations hold even in these extreme gravitational environments. The binary pulsar system discovered by Russell Hulse and Joseph Taylor in 1974 was one of the first systems where these effects were measured. The two neutron stars in that system orbit each other in an intense gravitational dance, and the timing of the pulsar signals provided the first indirect evidence for gravitational waves, ripples in spacetime itself. Their observations confirmed general relativity's predictions so precisely that Hulse and Taylor were awarded the Nobel Prize in Physics in 1993. There is another effect connected to gravitational time dilation that has been measured using signals passing near massive objects. In 1964, the physicist Erwin Shapiro predicted that a signal passing through a gravitational field would take slightly longer to travel than it would through flat spacetime. This is called the Shapiro delay. It happens because time runs slower in the curved spacetime near a massive object, and a signal passing through that region experiences the slower time, effectively taking a longer path through spacetime, even if its spatial path appears nearly straight. Radar signals bounced off planets on the far side of the Sun when the signal path passes close to the Sun take slightly longer to return than expected from simple distance calculations. The extra delay caused by the warped spacetime near the Sun has been measured repeatedly and matches general relativity's predictions with extraordinary precision. The Shapiro delay is gravitational time dilation made visible through the travel time of light itself. And there is yet another confirmation that spacetime curvature is physically real and not merely a mathematical convenience. In 2015, the LIGO Observatory directly detected gravitational waves for the first time. Gravitational waves are ripples in spacetime itself, produced when massive objects accelerate violently. Two black holes, each roughly 30 times the mass of our Sun, spiraled into each other and merged over 1 billion light-years from Earth. As they spiraled inward, orbiting each other faster and faster, they stirred spacetime into waves that radiated outward at the speed of light. Those waves traveled across the universe for over 1 billion years and arrived at Earth as unimaginably faint stretches and compressions of space. LIGO detected them by measuring changes in the length of its 4-kilometer laser arms that were about 1,000th of the width of a proton. This detection was monumental. It confirmed that spacetime is a real, physical, dynamic thing that can ripple and wave and carry energy across the universe. The same spacetime whose curvature causes gravitational time dilation is not a mathematical abstraction. It is a physical fabric that can be stretched and squeezed and detected with instruments. Since that first detection, LIGO and its partner observatories Virgo and Kagra have detected dozens more gravitational wave events, each one confirming that the spacetime Einstein described is the spacetime we live in. Now let us take the final step. Beyond white dwarfs and neutron stars lies the most extreme gravitational object in the universe, the black hole. A black hole forms when matter is compressed so completely that its gravitational field becomes inescapable. No force in nature can prevent the collapse. The matter falls inward past a boundary called the event horizon, and from that point, nothing, not matter, not light, not information of any kind, can escape back out. The event horizon is not a physical surface. It is not a wall or a membrane. It is a boundary in space-time, a point of no return defined entirely by the curvature of space-time geometry. The first mathematical description of a black hole came from Karl Schwarzschild, a German physicist who solved Einstein's field equations in 1916, just months after Einstein published general relativity. Schwarzschild found a solution describing the space-time geometry around a perfectly spherical, non-rotating mass. His solution, now called the Schwarzschild metric, describes exactly how space-time curves around such an object. And embedded in that solution is a radius at which something extraordinary happens. At a specific distance from the center, now called the Schwarzschild radius, the curvature of spacetime becomes so extreme that the escape velocity equals the speed of light. Inside that radius is the event horizon. And the behavior of time near the event horizon is where gravitational time dilation reaches its most extreme expression. As you approach the event horizon of a black hole, time dilation increases without limit. A clock falling toward a black hole ticks slower and slower relative to a clock far away. The closer it gets to the event horizon, the slower it ticks from the distant observer's perspective. At 90% of the way to the event horizon, the falling clock is already running dramatically slower than the distant clock. At 99%, the difference is enormous. At 99.9%, it is staggering. And in the mathematical limit, as the clock reaches the event horizon itself, its time as measured by the distant observer slows to a stop. From the perspective of someone watching from far away, the falling clock takes an infinite amount of time to reach the event horizon. It never gets there. It just gets closer and closer, ticking slower and slower, the light it emits stretching to longer and longer wavelengths, shifting from visible light to infrared to microwave to radio waves, getting dimmer and redder and slower until it fades from detectability. The distant observer never sees the clock cross the horizon. It just asymptotically approaches it, fading into invisibility over an infinite stretch of time. But here is the part that bends the mind. From the perspective of the clock itself, from the perspective of someone falling with it, nothing unusual happens at the event horizon. This is the same principle we have been discussing throughout this entire story. Locally, time always feels normal. The falling observer's heart beats at its normal rate. Their watch ticks normally. their seconds feel like seconds. They cross the event horizon and notice absolutely nothing special about the moment of crossing. There is no barrier, no wall, no flash of light, no dramatic sensation. The event horizon is invisible from the inside. You would not know you had crossed it. The geometry of space-time is curved, severely curved, but it is still smooth. There is no discontinuity, no sudden change. The falling observer and the distant observer simply disagree, radically and irreconcilably, about how much time the journey takes. The distant observer says the journey to the horizon takes forever. The falling observer says it takes a finite and possibly quite short amount of time. And both are correct. They are measuring different things. They are measuring proper time along their own respective paths through space-time, and those paths are so different in the extreme curvature near a black hole that they accumulate vastly different amounts of time. This is gravitational time dilation taken to its ultimate extreme. The same effect that makes a clock on the ground floor disagree with a clock on the top shelf by a few quadrillionths of a second on Earth makes a clock near a black hole disagree with a distant clock by an infinite amount. The mechanism is identical. The geometry of space-time near mass causes different locations to accumulate different amounts of proper time. On Earth, the curvature is gentle and the differences are tiny. Near a black hole, the curvature is extreme and the differences become boundless. Black holes are not theoretical, they are observed objects. We have measured their effects on nearby stars, on orbiting gas, on light passing close by. At the center of our own Milky Way galaxy sits a supermassive black hole called Sagittarius E star. It has a mass of roughly 4 million times the mass of our Sun. Stars orbit it at tremendous speeds. The star designated S2 orbits Sagittarius E star once every 16 years, and at its closest approach, it comes within roughly 18 billion kilometers of the black hole, traveling at nearly 3% of the speed of light. Astronomers have tracked S2's orbit for decades and have measured both gravitational time dilation and gravitational redshift in the light it emits as it swings through the intensely curved space-time near the black hole. The measurements match general relativity's predictions precisely. In 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow, the dark region surrounded by glowing gas around the supermassive black hole in the galaxy M87. That black hole has a mass of roughly 6.5 billion times the mass of our Sun. The image confirmed the size and shape of the event horizon region exactly as general relativity predicted. Then, in 2022, the same collaboration released an image of Sagittarius E star itself, the black hole at the center of our own galaxy. These are not distant abstractions. They are photographs and measurements of space-time curvature so extreme that time itself is warped beyond recognition. Let me return to the falling observer for a moment, because there is a common misconception I want to correct. People often say that time stops at the event horizon of a black hole. This is misleading. Time does not stop for the person falling in. Their experience is continuous and finite. They fall through the horizon and continue inward. From their perspective, nothing freezes, nothing pauses. Their time keeps flowing perfectly normally. What happens is that the comparison between their time and a distant observer's time becomes infinite. The mismatch grows without bound. But mismatch is not the same as stoppage. Time stopping would mean that the falling person is frozen, that no physical processes occur, that everything halts. That is not what happens. Everything keeps happening for the falling person. They just cannot communicate it back to the distant observer, because light from the event horizon can never escape. The falling observer experiences time. The distant observer cannot see that experience. The disconnect is not in the flow of time, but in the ability to compare times across the extreme curvature. This distinction matters because it goes to the heart of what this entire story is about. Time stopping matching itself near gravity is always about comparison. It is always about what happens when you try to relate the flow of time at one location to the flow of time at another. Locally, at every single point in every gravitational field, no matter how strong, time passes normally. A second is a second. Physics works. Atoms vibrate. Hearts beat. Nothing is strange from the inside. The strangeness is entirely in the relationship between different locations. And near a black hole, that relationship becomes so extreme, so stretched by the severe curvature of space-time, that two observers can disagree about the passage of time by any amount. Not just hours or years, but potentially centuries, millennia, or eternity, depending on how close one of them is to the event horizon. There is one more aspect of extreme gravitational time dilation that deserves attention. Inside the event horizon of a black hole, the nature of space-time changes in a way that is difficult to describe in everyday language. Outside the horizon, you can move freely in space. You can go left, right, forward, backward. But time only moves in one direction, forward. You cannot revisit the past. Inside the event horizon, the roles of space and time effectively swap in a certain mathematical sense. The direction toward the center of the black hole, the singularity, becomes as inevitable as the forward flow of time is outside. Just as you cannot avoid moving forward in time out here, you cannot avoid moving toward the singularity in there. It is not that something is pulling you, it is that the geometry of space-time inside the horizon is structured so that every possible path, every trajectory through space-time, no matter what direction you try to move, leads toward the center. The singularity is not a place in space. It is a moment in your future, an unavoidable one. You will reach it not because a force drags you there, but because the space-time inside the horizon simply does not contain any paths that lead anywhere else. At the singularity itself, according to general relativity, the curvature of space-time becomes infinite. Density becomes infinite. The equations break down. This is generally understood to mean not that infinite density actually exists, but that general relativity has reached the limit of its validity. At the singularity, quantum gravity effects should dominate, and we need a theory of quantum gravity to understand what actually happens there. We do not yet have such a theory, so the singularity remains an open question, a place where our understanding of space-time and time dilation reaches its limit. Let us step back now and look at the full picture. We started this journey with two clocks on a shelf, one a little higher, one a little lower. They disagreed by amounts so small you would need the most sensitive instruments in human history to detect them. Then we zoomed out. We saw that GPS satellites must constantly correct for the fact that time runs at a different rate in orbit than on the ground. We saw that the Pound-Rebka experiment measured the gravitational redshift of light climbing just 22 meters through Earth's field. We saw that velocity and gravity both change the rate of time, and that both effects come from the same underlying reality, the geometry of space-time. Then we pushed into extreme environments. White dwarfs, where gravitational redshift has been measured in starlight that travelled years to reach us. Neutron stars, where months of difference accumulate annually between the surface and distant space, and where pulsar timing confirms general relativity with extraordinary precision. Gravitational waves, detected by instruments sensitive enough to measure distortions smaller than a proton, confirming that space-time itself is a dynamic physical entity that ripples and rings when massive objects collide. And finally, black holes, where the effect becomes infinite at the event horizon, where the mismatch between a falling observer and a distant observer grows without any bound. Through all of this, the mechanism has been exactly the same. Mass curves spacetime. Curved spacetime has different amounts of proper time at different locations. Clocks at different locations measure different elapsed times, because the spacetime they are embedded in has a different geometric structure. This is not a metaphor. This is not an analogy. This is the literal physical description of how the universe works. Einstein's field equations of general relativity are geometry equations. They describe the shape of spacetime the way Euclidean geometry describes the shape of flat surfaces. And just as a curved surface has different properties at different points, curved spacetime has different amounts of time at different locations. The deepest lesson of gravitational time dilation is this: time is not separate from the universe. Time is not a backdrop against which events play out. Time is part of the fabric of reality, woven into spacetime, shaped by the presence of mass and energy. Where that fabric is curved, time behaves differently. Where the curvature is gentle, the differences are tiny. Where the curvature is extreme, the differences are enormous. But the effect is always there, at every scale, in every gravitational field, from the space between your head and your feet to the edge of a black hole's event horizon. You carry this effect with you every moment of your life. Right now, time is passing at a slightly different rate at every height in the room you are sitting in. The difference is so small that it has no practical consequence for your life. But it is real. It has been measured, and it has been there every moment of your existence, whether you knew about it or not. Every morning you have ever woken up, the clock on your bedside table experienced a fractionally different amount of time than the clock on the wall above it. Every time you have climbed a flight of stairs, you have walked into a region of space-time where time flows at a very slightly faster rate. Every time you have descended, you have moved into space-time where time flows a very slightly slower rate. The effect was there when you were born. It was there during every meal you have ever eaten, every conversation you have ever had, every night you have ever slept. Gravity has been quietly shaping the flow of time around you for your entire life. You just never had a clock precise enough to notice. And it is not only Earth. Every massive object you have ever been near has warped time in its vicinity. The building you live in warps space-time, though by an amount so small it is beyond any measurement we could conceivably make. The ground beneath your feet warps it. The moon warps it. The sun warps it enormously. And the planets move through that warped space-time, following geodesics, tracing the straightest paths through curved geometry, their clocks ticking at rates set by the space-time they are passing through. Everywhere in the universe, wherever there is mass, time is being shaped. It is being curved. It is being made uneven. And it has been this way since the first atoms formed, since the first stars ignited, since gravity first gathered matter into clumps and curved the space-time around them. The universe has never had a single uniform flow of time. There has never been a moment in the history of the cosmos when all clocks everywhere ticked at the same rate. The unevenness of time is not a special condition. It is the default state of a universe filled with matter. This tells you something profound about the universe you inhabit. It tells you that time is not fixed. It is not absolute. It is not the unchanging stage Newton imagined. It is flexible. It is geometric. It responds to the presence of mass. And it responds in a way that is precisely described by the most successful theory of gravity ever devised. A theory that was born from one man imagining a person falling from a roof. A theory that predicted effects so small they took half a century to measure. a theory that has passed every experimental test ever thrown at it, from laboratories on Earth to the surfaces of neutron stars to the edges of black holes. A theory that rewrote our understanding of what space and time actually are. Two clocks in different gravitational fields will disagree. Both are right. Neither is broken. The disagreement is not an error. It is a window into the geometry of spacetime itself. Every time two clocks fail to match, they are telling you the shape of the universe between them. They are measuring the curvature of reality. And that curvature, that warping of the very structure of space and time, is what we call gravity. That is why time stops matching itself near gravity. Not because something interferes with clocks, not because gravity exerts a force on the mechanism of timekeeping, but because gravity is the curvature of spacetime, and in curved spacetime, different locations have different amounts of time. The clocks are not disagreeing about what time it is. They are reporting, faithfully and accurately, that different amounts of time exist at their two locations. And both of them are telling the truth.